Imagine you have spent hours training a machine learning model to recognize images, classify text, or predict outcomes. You are very proud of what you have accomplished, but now you want to share it with others. Maybe you want to showcase your model's capabilities to your colleagues, or maybe you want to get feedback from the community. But how do you share a complex model in a way that is easy for others to understand? So that's where an interactive demos come in. An interactive demo is like a virtual showcase for your model where others can see it in action and interact with it in real time. In this video, we will show you how to build an interactive demo with your fine-tuned model using Gradio, which is a powerful tool for sharing and building NLP demos. So let's get started with understanding what is a fine-tuned model. Basically, it is a machine learning model that has been trained on specific tasks such as recognizing images or classifying text. Think of it like a chef who has perfected a recipe. That is the model that has been trained to do a specific job. Now, interactive demo is a way to showcase your fine-tuned model in a way that is easy for others to understand. It is like a virtual showroom where others can see your model in action and interact with it in real time. Now, why build an interactive demo? Basically, building an interactive demo is like a way to share your models with others and get feedback. It's like showing off your latest projects to your friends. You want to share it with others and want to hear what they think. Now, to build an interactive demo, you need to use the tools like Gradio, which is a powerful tool that makes it easy to build and share demos. So first of all, you'll need to import the Gradio into your code. Next, you'll need to load your fine-tuned model into Gradio. Then you will need to create a demo using Gradio interface. Finally, you'll need to add the interactivity to your demo, such as buttons or text inputs. Now, building an interactive demo has several benefits. Like interactive demos makes it easy for others to understand your model and how it works. Interactive demos allows others to provide feedback on your model, which can help you improve it. Also, it makes it easy to share your model with others, whether it is with colleagues or the wider community. For better understanding, let's understand it using the Python code. We'll run this code in Google Colab. So let's get started with Python coding. So this is the simplest Python code to build an interactive demo using Gradio. So here we are starting by importing the libraries and installing packages. So first of all, we'll install the transformer and Gradio library using pip. Then we'll import the pandas library, assign it the alias PD. Then we import the torch library, which is a popular deep learning framework. After this, we import two classes from transformers library, that is auto model for sequence classification and auto tokenizer, which are used for sequence classification task and tokenization respectively. Then we import the Gradio library, assign it the alias GR. Gradio is a library for building interactive web applications. After this, we import the train test split function from sklearn library, which is used to splitting the data into training and testing sets. Section 2 involves loading pre-trained model and tokenizer. So here we will first set the model's name variable to distillbird base uncaged, which is a pre-trained distillbird model. Then we load the pre-trained distillbird model using auto model for sequence classification class. From pre-trained method loads the model weights and configurations from Hugging Face model hub. Then we load the pre-trained tokenizer for the distillbird model using auto tokenizer class. After this, we create the dummy data set. So here this data line will create a dictionary containing two lists, text and the labels. So text list contains 5 text samples and the label list contains their corresponding labels, 1 for positive, 0 for negative review. Then we will convert this dictionary into the pandas data frame. Then comes the section 4, which is preparing the data set for fine tuning. So here we will split the data into training and validation sets using train test split function. The random state parameter is set to 42 for reproducibility and test size parameter set to 0.2, which means 20% of the data will be used for validation. Then we will reset the index of the train test series to avoid any potential indexing issues. After this, we reset the index of the well text series also. Then this train labels will reset the indexes of train label series. Well labels will reset the indices of well label series. Then we will create a custom dataset class. So here we are defining a custom dataset class, that is review dataset, that inherits from the PyTorch dataset class. So in this, we will first initialize the dataset class with 3 parameters: text, label and tokenizer. So here self.text means assigning the text parameters to instant variables, self.labels assign the label parameters to instance variables, self.tokenizer assign the tokenizer parameters. Then this def get item will define a method that returns a single data point from the dataset. Then it retrieves the text sample at index, then it retrieves the label at index IDX. Then encoding method will tokenize the text sample using encode plus method of tokenizer. Then it returns a dictionary containing the tokenized input IDs, attention, mask, and label. Here, this defining the length method will define a method that returns the length of the data sets. After this, we will create dataset instances and the data loader. So here we will create an instance of the review dataset class for the training data. Then we create an instance for review dataset for validation dataset. Set the batch size to 16. Create data loader for training set with batch size of 16. Shuffling enabled. Then this val loader will create a data loader for validation dataset. Then in the section 7, we will fine tune the model. So here we will first set the device to use for training, either a CUDA device or CPU. Then move the model to specified device. Define the loss function as cross entropy loss. Define the optimizer as Adam optimizer. Then loop through the 5 epochs of training. Set the model to training mode. Initialize the total loss to 0. Loop through the training data loader here. Then retrieve the input IDs from the batch and move them to the device. Then this attention mask line will retrieve the attention mask from the batch, move it to the device. Labels line will retrieve the labels from the batch, move them to the device. Then optimizer.0grad zeros the gradients of optimizers. Then it passes the input IDs, attention mask, and label to the model. Then loss is equals to output.loss. So it will retrieve the loss from the output model. Loss.backward will compute the gradient of the loss with respect to the model parameters. Optimizer.step updates the model's parameter using gradients and optimizer. Then this total loss accumulates the total loss and print the epoch number and average loss. Next, set the model to evaluation mode. So here in this evaluation mode, we are disabling the gradient computations. And then we are initializing the total correct predictions to 0, then looping through the validation data loader, then retrieving the input IDs from batch, moving them to device. Next, this attention mask line, retrieve the attention mask from batch, move them to the device. Then output line, pass the input IDs and attention mask to model. Logits line, retrieve the logits from model, then compute the predicted label by taking the argmax of logics, accumulate the total current predictions, compute the validation accuracy, and print the epoch number and validation accuracies. Then we will define the prediction function here. So here we are defining a function that will take in a text input and return the predicted label. Tokenize the input text using encode plus method of tokenizer. Move the input IDs to devices. Move the attention mask to device. Pass the input IDs and attention mask to the model. Retrieve the logits from output model. Compute the predicted label by taking argmax of logic and return the predicted label as scalar value. Then in section 9, we will create the Gradio interface. So here this demo line will create a Gradio interface with the predict function as input function. So fn specifies the input function as predict, input specifies the input type as text, output is equals to label specifies the output type as label. Then set the title of interface, set the description of interface. And finally, it will check if the script is being run directly, then launches a demo.launch will launch the Gradio interface. So by running this code in Google Colab, we'll get the results like this. So where we are getting the losses and validation accuracy for each epoch. And here we can check the sentiment of the text. So let's write some text and check whether it can give it sentiment or not. So here 1 means it has a positive sentiment. So this way you can also make this sentiment analysis model at your end by running this code directly in the Google Colab. And that's the wrap. Building an interactive demo with your fine-tuned model is like showcasing your masterpiece to the world. You have put in the hard work to train your model. Now it's time to share it with others. So with Gradio, you can create a demo that is easy to use, interactive and visually appealing. So whether you are a researcher, developer or enthusiast, building a demo is a great way to share your work and get feedback from others. So don't be shy. Share your demo with the world and see how others react to your creations. Who knows, you might just inspire others to build something amazing too. Thank you.